Everyone, today we are going to discuss about the refraction through a glass slab. Glass slab, you know very well that it is a transparent kind of thing, so light ray can easily pass through it. And in a shape, it will be a rectangular one, where the opposite sides will be, equal and also parallel to each other. Okay. So now first of all, let me tell you how you can draw the image of a light ray which is passing through a glass slab. Then we will go for proving it. So first of all, let me take one rectangular shape. So we have taken a rectangular shape here, and let me first draw one normal on it. Okay. We have taken the normal. This normal I have to take, in a straight manner. Just a minute. Okay, now it's look like a proper normal here. So let me take one incident ray on it. Okay, we will take a incident ray. Let me show it by the another pen. It'll be easy for all of you. So I have taken the orange pen for this. This is the incident ray for us. Okay, now this is the first boundary. Okay, first boundary where the light ray is about to pass from air to glass, because it's a glass slab. So we will separate the boundaries. This is the boundary 1 and this will be the boundary 2nd. Okay, two boundaries we have, boundary 1st and boundary 2nd. So nothing is there outside, so we can suppose it is the air. So from air into the glass, the light ray is about to enter, and again what will happen, from glass to air it will emerge. So right now we are talking about that. We'll just talk about first the incident ray here. Let me show you the incident ray. So this arrow shows that is the incident ray over there, which is coming from air to glass. The incident ray is I over there. Since we know that from a rarer medium, because relatively air is a rarer medium than the glass, because glass is a denser medium with respect to the air, that's why the light is about to bend. Okay, because we know the light will get bent into a denser medium. So whatever the angle I will be there, the refractive angle will be always less than it, because the light is about to bend. So if you talk about the normal ray, that without any deviation, okay, it should go like that, without any deviation. This is the imaginary one, just because it will not go like that. It will always bend towards the normal whenever it will enter from rarer to denser, that means from air to glass. So let me bend it. Suppose that the light is bending up to that much. Clear? Now this is the refractive angle called R. Okay. Now suppose that in the second boundary where it is reaching, we have to take one more normal over there. Okay, we have to take one more normal over there, like that, is it? So let me take this as a perfect normal, so that I can make a perpendicular to it, like that. Yes. Okay, now this refracted ray which is incoming through that process, okay, for the second boundary it will act as an incident, because now this ray is incident on it. Okay, let me take it R dash, okay, which is equal to the R. Why? Just because this normal and this normal, they both are at 90 degree with respect to the parallel sides of the glass slab. Clear? So R will be equal to the R dash here we can get. Okay, also we can say it is an alternate angle, easily we can do that. Okay, so now the light ray is actually incident on the second boundary as a R dash. So finally when the light ray will goes out from the glass itself, the ray is not a refracted now, it will be the emergent ray. It will be known as emergent ray, that is called E. Okay, so finally the light ray will go away from the normal just because now the light ray want to escape from the denser medium to the rarer medium. Okay, that means the emergent ray, the final ray which is going outwards from the glass slab, which will be the angle between them will be more than the r dash over there. So let me take the emergent ray. It will go away from the normal. Sorry, yes, it will go away from the normal like that. Is it? So we will see that the original path, okay, that is called E here, it is the emergent ray, that is away from the normal. Here that E will be obviously greater than the r dash. Now here we have to prove that I was equal to E, okay, so that we can say that the virtual line, which is actually we are assuming that without deviation it can go like that, and after second refraction, that means from the second boundary, this line and this line will be parallel to each other. And why it will happen? Just because of angle E is equal to angle I over there. Okay, that we have to prove now. So we will use the Snell's law for that, for proving that. Okay, so the next page I will go. Since the light ray was coming from air to glass in the first half, okay, this one, so we can write like that here, that A and D or A and G we can write, because glass it is entering. So the refractive index of glass with respect to air, because from air to glass the light is incoming, so we can write sin I upon sin R. This is the first equation for us. Clear? A and G means what? The light is incoming from the air to glass, and in other words we can say with respect to the refractive index, that refractive index of glass with respect to air, which equal to sin I by sin R. This is the first equation for us, and this was the first boundary. First boundary. Now for the second boundary, what we can write? For the second boundary it is like that. Now the incident ray for the second boundary is r dash, and the emergent ray is the E over there. Okay, so let me write for that equation, because now light rays goes out from the inner side to the outer side. Inner side is the glass and outer side is the air. That means now we have to write that G and A, because right now we will talk about the refractive index of air with respect to glass, because light is now incoming from the glass and go outside with the air. We can write here sin r dash divided by sin E. This is equation 2. Clear? Because now according to Snell's law, the incident ray for the second surface is what? Second boundary is the r dash, and the emergent ray, that means the refracted ray, is E over there. Now we know the relation between A and G and A is just inversely proportional, just because the A and G is equal to 1 upon GNA. A and G is equal to 1 upon G and A. Okay, we know that from relative refractive index theory. We know that A and G is equal to G and A. Okay, and how it's coming already I told you, so it's not a big deal for us right now, because A and G is supposed to be Ng upon Na. Okay, and then we will go for that GNA is Na upon Ng. It's just 1 upon something. Okay, so now we will put the equation 1 and equation 2 here, because we know the value of A and G and GNA in the terms of I and R. Okay, so we can put the values here. So we can write one more thing here, just like that. Once again, A and G is equal to 1 upon G and A. Okay, so by using equation 1 and equation 2. What we can get now? For A and G was what? Sin I by sin R. Sin I upon sin R is equal to 1 upon GNA was what? GNA was sin R dash upon sin E. Sin R dash upon sin E. Okay. In a simplified word, we can write that sin E upon sin R dash. Okay, that we can write. We know that R is equal to the R dash is because of alternate angles. Okay, in the figure you can see these are the alternates angle. That's why R equal to R dash already we have written over there. Okay, so finally we will cancel each other. That sin I, that sin R is equal to sin E upon sin R dash. Okay, so we can cancel this one and this one. Okay, and we finally get that sin I is equal to sin E. By compare, we can write that I equal to E here. Okay, so finally we have proved that the incident angle on the boundary 1 is equal to the emergent angle on the boundary 2. So hence we can also prove that the virtual, our assumptions that it will be a parallel to the real line, which is after 2 times of reflection we can get that this will be equal to each other. Okay, and they are parallel to each other. Angles are equal and the lines are parallel to each other. Okay, so I hope this is very clear to all of you. Thank you. Bye bye.